In this video, I'm going to talk about finite state machines as a way to specify and describe a protocol. Finite state machines are really useful as a technique because they're a simple way to describe how your protocol responds to events and the actions that it takes. And often when you're sitting down to design a protocol, it's useful to walk through a finite state machine as to what's going to happen. It'll let you discover error cases, and it'll let you think through even how you might want to structure its implementation and structure its design. So for those of you who have a background in sort of the more theoretical side of computer science, finite state machines are probably a basic concept, but I'll just give a review of them regardless. So first of all, a finite state machine, of course, the first thing you have are states. States in which the protocol can be. And there's a finite number of them, and so you can count them. So in this case, say we have three states, state 1, state 2, and state 3. Now in addition to states, you have transitions between them. And the way you describe a transition is usually you draw an arrow, say here from state 1 to state 2. And on top, you state what is the event that could cause the state transition, cause the protocol to go from state 1 to state 2. And then below this line, you say what are the actions that the protocol will take on that state transition. And so you can have multiple events and actions, but generally there will only be one edge between any two pair of states. So for example here, we could of course have state transition within the state with some event and some action. And we could have, say, a state transition from state 3 to 2 with some event and some action, and a state transition from state 3 to 1 with some event and some action. And even just looking at this, without knowing what these events and actions are, we can see, for example, that once the protocol transitions out of state 1 into state 2, or rather once it's in state 2, it can never escape from state 2. Furthermore, whereas state 3 can transition back to state 1, it can transition to state 2. Again, you'll be stuck then at state 2. There's only one edge coming out of state 2, and it keeps the protocol in state 2. So even just looking at the events and actions, we can see at a high level, aha, this protocol, once it goes to state 2, will never leave it. So even at this high sort of picture level, we can see something important about the protocol. So that's the abstract. Let's walk through. This is a simple finite state machine of how you might represent an HTTP request. So if you recall, what's going to happen is back from the lectures about HTTP, the videos about HTTP, the way it works is I have some client, and let's say we have no connection open. We're just starting at the beginning. So we're in this beginning state of idle. Then at some point, we get a URL that we want to request. And so we get a request for some URL, say from our browser, is the event. And now the action is we're going to try to open a connection to the web server corresponding with that URL. So now we're in a second state, the opening state. And we're now waiting, hopefully this connection will open. Well, let's say that the connection doesn't open. Let's say that the connection fails. We can't, the URL is bad. Well, we're going to go back to the idle state. So event is URL bad, or sorry, connection bad, connection failed. We'll go back to the idle state, and so we will clean up connection. Clean up connection. If we had some state or some memory allocated, we'll clean up all that. So here, try to open a connection. If the connection fails, we then go back to the idle state. Now what if the connection succeeds? So now we have connection succeeds, connection opened. Right? What's the action? Well, we're going to send a request. We're going to actually send this request. Right? And now we're in the requesting state. Well, say one of three things could happen. The connection could break. So for some reason, the web server crashes or something happens, connection breaks. We'll go back to the idle state and clean up the connection. It could be that the request is malformed. For whatever it is, this URL that we requested, it's no good. In that case, we might actually connection breaks, or we get an error code. If we get an error code from the server, we could also just close the connection down and say, oh, bad request, no good. Or another event that can occur is we get a response, receive response. And the action we take is pass response, or pass response to application. And we're now entering into this state, which is the response state. So response, or the response state. And then once we're in the response state, okay, we've done a request, received the response. Now we close the connection and go back to idle. Right. So this could just be, there's no event. Once we enter the response state, clean up connection. And so here's a pretty simple finite state machine where it's basically a linear progression of states. Try to open a connection, send a request, get a response. And in the case, there might be some error conditions which cause us to transition back to the idle state. So this is a pretty simple finite state machine, this linear sequence of steps, where each step there's some errors and they cause you to all go back to the idle state. Finite state machines can be significantly more complex than this one. And so later in future subject matter, future videos, we're going to see some examples of that. But just give you a hint, right? And I hope this isn't too daunting. So this is the finite state machine for opening for a TCP connection, where this part of the finite state machine up top is opening a connection, and this part of the finite state machine down below is closing the connection. This is just a picture from Wikipedia. And so you see, like, you start in a closed state, and then depending on whether or not you try to open a connection actively or a server listening for a connection, do different transitions. Here's where the connection, the TCP connection has been established, and you can actually exchange data until the closed down sequence starts. So we'll go over this finite state machine in greater detail when we cover TCP, but one of the points here to make is that there's all kinds of different edges here and all kinds of different states. And one of the most important things that comes out in a finite state machine is you want to consider all of the different possible events and how you might respond to them. So, for example, here, when you look at the close transit, what's happening in this close sequence, there's all these different orderings in which particular events can happen. It can be one side sends what's called a fin before the other, or the other side sends it first, and the system responds differently. And so one of the marks of a good finite state machine is that you look at all the possible events that could occur in your protocol or in your system. And for each state, you want to define what happens on that event. The last thing you want to have happen is you don't consider, well, what if I'm in the open state, if I'm in this opening state, and suddenly I get a packet that looks like this. Now, it's not part of the normal sequence of operations, so I didn't consider it, but then suddenly it happens and your protocol crashes or something goes wrong or it behaves strangely because you didn't think of specifying the behavior. So in fact, this depiction of the TCP finite state machine doesn't show the full picture. Like, you can notice it doesn't say what happens when you get a fin message while in one of these states. It end up transitioning over here. But when you're thinking through the protocol and really trying to specify its exact operation, you want to think through every state, what will happen in response to any given action or any given event. So, like, if we go back to this HTTP request, right? One of the things I didn't consider is what happens if you open a connection, the connection's been opened, and we get a response before we send a request, right? Before a request, say, has been sent, or what happens if the response is an invalid response? Like, here's a possible bug in my finite state machine. Here I just say receive response. I don't say receive correct response. Something I might do is actually say, correct. response. And then what I want to do is add an edge and say receive incorrect response. That is a response which is not correlated with my request, like what happens if there's some bug in the server, and cleanup connection. Similarly, here there's just this receive response. I could also expand out this receive response to talk about, well, what happens if I receive an incomplete response? Like here, what happens? Do I just stay waiting here forever if the response only comes in partially? Or you could imagine that you have some kind of timeout, and so there might be a timeout edge here, right? Timeout. If it takes too long for the response to arrive. And so often developing finite state machines for protocols is an iterative process. You realize there's an error condition you hadn't considered, and you need to sort of further refine your finite state machine design. As you get more experience doing this, of course, you consider all of these a priori rather than having to keep on going back, such that you can design a cleaner, simpler finite state machine from the beginning, and then design a cleaner, simpler protocol. And it makes it then easier to implement and also easier to check and easier to debug.